Number 41 is another finding from Trail of Bits audit of the origin dollar, where it was another high severity finding related to data validation. OUSD total supply could be arbitrary and even smaller than user balances because the OUSD token contract allowed users to opt out of rebasing effects, at which point their exchange rate would be fixed and further rebases would not have any impact on token balances until the user opts back in. The recommendation was to specify all common invariant violations for users and other stakeholders in the short term and redesign the system in the long run to preserve as many common invariants as possible. This is related to aspects of token handling in number 159, data validation issues in number 169, and numerical issues in 170 we discussed in Security Pitfalls and Best Practices 201 module. Number 42 is a finding from Trail of Bits audit of yield protocol, where it was a medium severity finding leading to undefined behavior. The issue was that the flash minting feature from the FY DAI token could be used to redeem an arbitrary amount of funds from a mature token in the context of the protocol. The recommendation was effectively to disallow flash minting to prevent attackers from gaining leverage to manipulate the market and break internal invariants. This is related to aspect of flash minting in number 121 and scarcity issues we discussed in number 186 of Security Pitfalls and Best Practices 201 module. Number 43 is another finding from Trail of Bits audit of yield protocol, where it was a high severity finding related to access control, in which a lack of chain ID validation allowed signatures to be reused across forks. YDAI implemented the draft ERC 2612 standard via the ERC20 permit contract, which allows a third party to transmit a signature from a token holder that modified the ERC20 allowance for a particular user. These signatures used in calls to permit in ERC20 permit did not account for chain splits, and as a result, if the chain forked after deployment, the signed message would be considered valid on both forks. The recommendation was to include the chain ID opcode in the permit schema to make replay attacks impossible in the event of a post-deployment hard fork. This is related to aspects of cryptography issues we discussed in number 174 of Security Pitfalls and Best Practices 201 module. Number 44 is a finding from Trail of Bits audit of Hermes, where it was a high severity finding related to data validation, in which lack of a contract existence check effectively allowed token theft. The recommendation was to check for contract existence in safe transfer from function before interacting with the contract. Recall that the Solidity documentation warns about low-level call, delegate call, and call code returning success even if the called account is non-existent. This is related to number 87 of Solidity 101 module, number 38 of Security Pitfalls and Best Practices 101 module, and the broader aspects of external interaction issues we discussed in number 174 of Security Pitfalls and Best Practices 201 module. Number 45 is another finding from Trail of Bits audit of Hermes, where it was a medium severity finding related to timing, in which there was no incentive for bidders to vote earlier. Hermes relied on a voting system that allowed anyone to vote with any weight at the last minute, and there was no incentive for users to bid tokens well before the voting ends. This allowed users to bid a large amount of tokens just before voting ended, and so anyone with a large fund could decide the outcome of the vote. With all the votes being public, users bidding earlier would be penalized because their bids would be known by other participants, and an attacker could know exactly how many tokens would be necessary to change the outcome of the voting just before it ended. The recommendation was to explore ways to incentivize users to vote earlier by considering a weighted bid with weight decreasing over time, and also to recognize the many challenges of blockchain-based online voting. This is related to timing issues of number 177 and incentive issues of number 187 that we discuss in Security Pitfalls and Best Practices 201 module. Number 46 is another finding from TaylorBit's audit of Hermes, where it was a high severity finding related to access control. The system used the same account to change both frequently updated parameters and less frequent ones, which is an error-prone and risky design because it increases the severity of any privileged account compromises. The recommendation was to use a separate account to handle updating the less frequently changed parameters, and in the long term to design and document the access control architecture carefully. This is related to access control aspects discussed in number 148, 149 and 172, and also the principle of least common mechanism we discussed in number 194 of the Security Pitfalls and Best Practices 201 module. Number 47 is another finding from TaylorBit's audit of Hermes, where it was a high severity finding related to data validation. The issue was the one-step procedure for critical operations that is error-prone and can lead to irrecoverable mistakes. For example, the setter for the white hat group address sets the address to the provided argument. If the address is incorrect, then the new address would take on the functionality of that role immediately, leaving it open to misuse by anyone who controlled that new address. Or if the new address was one without an available private key, it would lock access to that role forever. The recommendation was to use a two-step procedure for all such critical address updates to prevent irrecoverable mistakes. This is related to the two-step change of privileged roles we discussed in number 50 of Security Pitfalls and Best Practices 101 module and number 162 of the Security Pitfalls and Best Practices 201 module. Number 48 is another finding from TaylorBit's audit of Hermes, where it was a high severity finding related to configuration, in which Hermes auction protocol and withdraw delayer had initialization functions that could be front run. Due to the use of the delegate call proxy pattern, these contracts could not be initialized with the constructor and had initializer functions, all of whom could be front run by an attacker, allowing them to initialize the contracts with malicious values. The recommendation was to either use a factory pattern that would prevent front running of the initialization, or ensure deployment scripts are robust to prevent front running attacks by atomically deploying and initializing. This was discussed in number 192 of Solidity 201, number 21 and number 95 of Security Pitfalls and Best Practices 101 module, and number 143 and 166 of the Security Pitfalls and Best Practices 201 module. Number 49 is a finding from TaylorBit's audit of Uniswap v3 protocol, where it was a medium severity finding related to data validation, in which missing validation of owner argument in both the constructor and set owner functions could permanently lock the owner role if a zero address or incorrect address were to be used. That would have forced an expensive redeployment of the factory contract, followed by re-addition of pairs and liquidity, which could have led to reputational damage among its users and potentially concurrent use of two versions of Uniswap. The recommendations were: 1. Designate message sender as the initial owner and transfer ownership to the chosen owner after deployment. 2. Implement a two-step ownership change process through which the new owner needs to accept ownership. And 3, if it was needed to be possible to set the owner to zero address, implement a separate renounce ownership function. This is related to the missing zero address validation we discussed in number 49 of Security Pitfalls and Best Practices 101 module, and also the two-step change of privilege roles we discussed in number 50 of the same module, along with number 162 of the Security Pitfalls and Best Practices 201 module. Number 50 is another finding from TaylorBit's audit of Uniswap v3 protocol, where it was a high severity finding related again to data validation, in which an incorrect comparison in the swap function allowed the swap to succeed even if no tokens were paid. This issue could be used to drain any pool of all of its tokens at no cost. The check inside one of the requires in that function was incorrect because it used greater than or equal to instead of less than or equal to operator. The recommendation was to simply replace the greater than or equal to operator with less than or equal to operator in that required statement. This is related to the aspect of conditionals we discussed in number 147 and the broader aspect of data validation issues in number 169 of Security Pitfalls and Best Practices 201 module. Number 51 is another finding from TaylorBit's audit of Uniswap v3 protocol, where it was a medium severity finding related to denial of service in the swap function, which relied on an unbounded loop that an attacker could exploit to disrupt swap operations by forcing the loop to go through too many operations and potentially trapping the swap due to out of gas exception. The recommendation was to bound the loops and document the bounds. We've discussed concerns with calls within loops leading to denial of service in number 43 of Security Pitfalls and Best Practices 101 module, and more broadly, the denial of service issues in number 176 and gas issues in 182 of Security Pitfalls and Best Practices 201 module. Number 52 is another finding from TaylorBit's audit of Uniswap protocol, where it was a medium severity finding related to timing and access control, where a front run on Uniswap v3 pool initialize function allowed an attacker to set an unfair price and to drain assets from the first deposits. There were no access controls on the initialize function, so anyone could call it on a deployed pool. Initializing a pool with an incorrect price allowed an attacker to generate profits from the initial liquidity provider's deposits. The recommendation was to 1. Move the price operations from initialize to the constructor, or 2. Adding access controls to initialize, or 3. Ensuring that the documentation clearly warns users about incorrect initialization. This was discussed in number 192 of Solidity 201, number 21 and number 95 of Security Pitfalls and Best Practices 101 module, and number 143 and 166 of the Security Pitfalls and Best Practices 201 module. Number 53 is another finding from TaylorBit's audit of Uniswap v3 protocol, where it was a medium severity finding related to application logic, where swapping on a tick with zero liquidity enabled a user to adjust the price of one way of tokens in any direction, and as a result, an attacker could set an arbitrary price at the pool's initialization, or if when the liquidity providers withdrew all of the liquidity for a short time. The recommendation was to ensure a design where pools don't end up in unexpected states or warn users of potential risks. This is related to business logic issues discussed in number 191 of Security Pitfalls and Best Practices 201 module. Number 54 is another finding from TaylorBit's audit of Uniswap v3 protocol, where it was a high severity finding related to data validation, in which failed transfers may be overlooked due to lack of contract existence check. Transfer helper Safe Transfer performed a transfer with a low level call without confirming the contract's existence. As a result, if the tokens had not yet been deployed or had been destroyed, Safe Transfer would still have returned success even though no transfer had actually executed. The recommendation was to check for contract existence before interacting with the contract. Recall that the solidity documentation warns about low-level call, delegate call, and call code returning success even if the called account is non-existent. This is related to number 87 of Solidity 101 module, number 38 of Security Pitfalls and Best Practices 101 module, and the broader aspects of external interaction issues we discussed in number 174 of Security Pitfalls and Best Practices 201 module. Number 55 is a finding from TaylorBrid's audit of DFX protocol, where it was a high severity finding related to undefined behavior, in which the left-hand side of an equality check had an assignment of the variable output amount, and the right-hand side of that check used the same variable. According to Solidity documentation, such a check constituted an instance of undefined behavior, and as such, the behavior of that code was not specified and could change in future releases of Solidity. The recommendation was to rewrite the if statement such that it did not use and assign the same variable in an equality check, and in general avoid undefined language usages. This is broadly related to the undefined behavior issues we discussed in number 179 of Security Pitfalls and Best Practices 201 module. Number 56 is another finding from TaylorBrid's audit of DFX protocol, where it was a high severity finding related to data validation, where certain functions returned raw values instead of converting them to numeraire values that it used for its internal arithmetic. Interchanging raw and numeraire values would produce unwanted results and may have resulted in loss of funds for liquidity providers. The recommendation was to change the semantics of such functions to return the numeraire balance instead of raw balance, and in the long term use unit tests and fuzzing to ensure that all calculations return the expected values. This is related to the broad aspect of data validation issues we discussed in number 169 of Security Pitfalls and Best Practices 201 module. Number 57 is another finding from TaylorBrid's audit of DFX protocol, where it was a medium severity finding related to data validation, in which the system incorrectly assumed that 1 USDC is always worth 1 USD without using the USDC to USD oracle provided by Chainlink, and therefore could result in exchange errors at times of deviation. The recommendation was to replace the hard-coded integer literal in the get rate method with a call to the relevant Chainlink oracle so as to ensure that the system is robust against changes in the price of any stablecoin. This is related to the broad aspect of data validation issues we discussed in number 169, and specifically the constant issues in number 184 of Security Pitfalls and Best Practices 201 module. Number 58 is another finding from TaylorBrid's audit of DFX protocol, where it was an undetermined severity finding related to patching, in which the system used a deprecated old version of the Chainlink price feed API aggregator interface throughout the contracts and the test. For example, the deprecated function latest answer was used, which is not present in the latest API reference aggregator interface v3. In the worst case scenario, the deprecated API could cease to report the latest values, which would very likely cause protocol liquidity providers to incur losses. The recommendation was to use the latest stable versions of any external libraries or contracts used by the code base as external dependencies. This is related to the broad aspects of configuration issues of number 165, external interaction issues of number 180, and dependency issues of 183 we discussed in Security Pitfalls and Best Practices 201 module. Number 59 is a finding from TrailerBit's audit of 0x protocol, where it was a high severity finding related to data validation, in which the cancel orders up to function could cancel future orders if it were called with a very large value, such as max UN256 minus 1. The recommendation was to properly document this behavior to warn users about the permanent effects of cancel order up to on future orders, or alternatively disallow the cancellation of future orders. This is related to the broad aspect of data validation issues we discussed in number 169 of Security Pitfalls and Best Practices 201 module. Number 60 is another finding from TrailerBit's audit of 0x protocol, where it was a high severity finding related to specification, in which there was a specification code mismatch for asset proxy owner time lock period. While the specification indicated that submitted transactions must pass a 2-week time lock before they were executed, the time lock period implementation did not enforce the 2-week period, but was instead configurable without any range checks, indicating that either the specification was outdated or that this was a serious flaw. The recommendation was to implement necessary range checks to enforce the time lock period described in the specification, or otherwise correct the specification to match the intended behavior. This is related to the broad aspects of system specification of number 136, tests of number 155, and clarity issues of 188 we discussed in Security Pitfalls and Best Practices 201.